Good morning, students. Today we start our today's lesson on operational amplifier. As I told you last day, that the name operational amplifier came into being sometime in 1960s, late 60s, when this amplifier was introduced in the market. That it was found that many complicated discrete circuits can be easily created or designed by using op-amps. So it is useful for many operations. That's why it is called operational amplifier, or now very shortly, op-amp. Now what it is basically? Op-amp basically is a very high gain, very high differential gain DC amplifier, AD. Differential gain, which we discussed in our last lesson, in nowadays integrated circuits that you get in the market, AD you can consider infinite, right? And this is a differential gain. It's not talking about, we are not talking about common mode gain, because if you give same input to the two terminals of the amplifier, the output will be zero. And it's a DC amplifier. I really invite your attention to this point, DC amplifier. That means if there is a DC input, that also is amplified at the output. All these days that you have learned common emitter amplifier, etc., so many things, mind it, all were signal amplifiers or AC amplifiers, because the DC output was always blocked, because DC quiescent output was of no use in case of signal amplifier. But op-amp is a DC amplifier. DC input is also amplified. Now, here I have shown you a picture. The picture is not very clear. Actually, I have scanned it from a textbook. This is a complex picture of a IC741 op-amp. In fact, this also to me appears to be very simple. Present as the operational amplifier ICs you get in the market, they are very complicated. I showed you this picture just to show you, just to give you an impression what is there inside this IC. There are so many components inside this IC. What is there inside? You forget it. There are so many components. Now we can describe an operational amplifier by this basic structure. There is an input stage, which is a difference amplifier. The same difference amplifier that we learned yesterday. There are two inputs, one here, one here. The output of this difference amplifier is the amplification of the difference of these two inputs. Now this difference is outputted here, gain with gain, and then there is a very high gain linear amplifier, where this output is amplified thousands of times, or maybe hundreds of thousand times it is amplified by this high gain amplifier. Right? Now, the design of this difference amplifier, a high gain amplifier, is such that output, there is a level shift, DC level shift, due to the quiescent point of quiescent values or quiescent current values of earlier two stages, which is DC level shift. Actually, suppose there is, you give 5 volt here and you give 5 volt here. So your difference is 0. The output here should be 0. But due to the design of this circuit, output is not 0. Say output is 1.2 volt. And this shift is known. And there is a level shifter which shifts that level by, again, minus 1.2, so that it becomes to 0 once again. And then there is an output amplifier which produces sufficient current so that it can drive the external circuits. So these are the 4 basic stages of this operational amplifier. You just need to remember these 4 stages. Forget about what is there inside. Then there are a few other things. This is the equivalent circuit of this whole operational amplifier. There are the 2 inputs, right? And there is a equivalent input impedance, Rin, which is practically infinite. For all normal calculations, it is concerned infinity. And there is a negative input, which is called inverting input. There is a positive input, which is called non-inverting input. In fact, Vd is V1 minus V2, not V2 minus V1, because V1 is the positive input. Vd is V1 minus V2, which is amplified here. This is the output VO. Now, any such circuit will have an output impedance, and this is just a schematic representation that output impedance is RO. And practically, all practical purpose, Rin is almost equal to infinity, RO is almost equal to zero. But I have shown you this, Rin and RO, just to emphasize that they're there, right? Next point is, there is a term in operational amplifier application which is always called virtual ground. What is it? See, as I said, its gain is almost infinity, right? So if you apply, say you apply the positive input, it is grounded, right? And say negative input is say minus 1 volt. Negative, they say input here is 1 volt. So 0 minus 1 volt is minus 1 volt input. Vd is minus 1 volt, 0 minus 1, right? Then what is the output? Will the output be minus infinity or plus infinity? It cannot happen. It cannot happen. In that case, this is an IC where you give 1 volt input and you get millions of megavolt output. Is that possible? That's not possible. Because the output is always limited to plus VCC and minus VCC. If you provide power supply by plus minus 10 volt, then output will be limited to plus minus 10 volt, right? It will be slightly less than 10 volts, say maybe plus minus 9.9 volt, like that. So since AD or differential gain is infinity and VO is limited to plus minus VCC. So this is always limited to plus minus VCC. This is not infinite. This can never be infinite. You cannot get 1 lakh volt output of a IC by providing only 10 volt input. This is unthinkable. So this is 10 volt. And since the gain is infinity, then what is Vd? Vd is 0. This means if the non-inverting terminal is grounded, then Vd will appear to be 0, will readjust itself to 0. That means this also will be at same potential of ground. This particular feature of operational amplifier, that if positive input is grounded, the negative input also appears to be grounded electrically, although you have not physically connected it to ground. It will be physically at 0 volt. If this is at 0 volt, this also will be at 0 volt. This being virtually at 0, this is called virtual ground. This term is very common in op-amp application. Sometimes they ask you what is virtual ground. If the non-inverting input is grounded, the inverting input also will appear to be grounded because it will be forced to 0 potential. And that is called virtual ground. Next is, what is the pin configuration? This op-amp 741 has 8 pins, right? The IC can be a rectangular IC, which is called DIL or DIP IC, dual inline package. It can be circular, it can be many shapes, but there will be always 8 terminals, right? Now, you know how to find out the terminal number of an IC. If there is an IC, you'll always find that there is a notch here, a little cut here. In that case, from the cut, on the left-hand side, it starts with 1. then go down 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 terminals of mono op amps. Of the ICs where only one op amp is there. But there are ICs where are dual op amps, quad op amps, like that. Their pin configuration will be different and you have to see the data manual. But mostly you will work with mono op amps. Now these pins are like this. Pin number 1 is offset null. I'll explain you what is offset null. Pin number 2 of the IC is always the inverting input, negative input, that is this input. This is pin number 2. Pin number 3 is the positive input, that is this input. Pin number 4 is minus VCC, that is connected to minus 10 volt. Pin number 5 is offset null. I'll explain you what is it. Pin number 6 is always the output. Pin number 7 is the positive supply voltage. Pin number 8, there is no internal connection. But there has to be 8th pin, otherwise it will not fit into the socket. For the sake of symmetry, 8 pin. If there are 4 pins on the left-hand side, there has to be 4 pins on the right-hand side. Now, what is offset null? We have seen this, we have said that this common mode gain of this amplifier is 0. That means if you apply 1 volt here and also 1 volt here, that means 1 volt at both terminals, then common mode value is 1 plus 1 divided by 2, that is half volt. And common mode gain is 0. That means output should be 0. But sometimes it may happen you find output is not 0. Output may be a few microvolt plus or minus. Right? Normally for our day-to-day work that doesn't matter. But if you are a scientist and you want really 0, then what do? Then you use this connection. You take a 10K potentiometer, connect its 2 ends between these 2 offset null terminals, terminal 5 and terminal 1, and the midpoint of the potentiometer you connect to minus VC, that is to minus power supply. And by adjusting this potentiometer, you can make the output to 0. Now, this is the configuration of old types, 741, which came into the market sometimes in the middle of 1960s. That means about 60 years ago. But in these last 60 years, there had been many improvements and developments in integrated circuitry. So in multiple ICs, multiple op-amp ICs, like say MC1458, where in one IC there are 2 op-amps, this offset null thing is not there. Because nowadays with the IC integration has become so developed, this offset normally does not exist, right? So this is the pin configuration. Now let us go to the application of an op-amp. The first application is the inverting amplifier. So where this is the op-amp, from output to the inverting terminal, you connect a resistor RF, and from inverting terminal, you connect a resistor R1 and give you input here, and the non-inverting terminal, you connect to ground. This very simple configuration gives you a very good amplifier, and that is why it's called operational amplifier. What is the gain of this closed loop circuit? See, this Rin is practically infinity. So there is practically no current in this direction. If that is so, then this current In and If are same, because no current flows in this branch. And since conventionally their directions are opposite, so In is equal to minus If. Now what is In? If this is at 0 volt, In is V in by R1. And if this is at 0 volt, then what is If? is V0 by RF, and there is a negative sign. So what is VO? Is equal to minus RF by R1 V in. So it is simple. There is a gain factor of RF by R1. So if you take a 10K resistor here and a 1K resistor here, your gain is 10. As simple as that, with a negative sign. That means if there is a positive input, output will be negative. Or if there is a sinusoidal input, output will be also sinusoidal, but with a reverse polarity, right? Now, in practice, this is not directly connected to ground. If you directly connect it to ground, there will be little offset output, very, very little, few microvolt. This you normally use a resistor here, and the value of the resistor is the parallel combination of R1 and RF. Is connected with the resistor R2. The value of R2 is R1 and RF. So if you are working in your laboratory, always use a resistor here whose value is parallel combination of these two. This is inverting amplifier. This is a non-inverting amplifier. The same amplifier, right? The same amplifier, only the input is given to the inverting input. And this resistor R1 is connected to ground. That is the only difference. Now, what is the gain of this? VD, difference voltage here, is 0. Right? So, the potential at the inverting input, that means here, also inverting input is also will be 0. So what is the current I in? This is at 0. Current I in is V in by R1. V in by R1. And IF is VO minus V in, because there is a potential here. VO minus V in by RF. Just solve these two equations, these two values, and since I in is equal to IF, just solve them. You find VO output is equal to 1 plus RF by R1 in. Here, inverting amplifier gain was RF by R1. Here, the gain is 1 plus RF by R1 with a positive sign. That is the only difference. Now, we shall see how they really work, right? Now, we shall see how they really work. Like this. We shall go to software simulation. This is the inverting amplifier and this is the non-inverting amplifier. Inverting amplifier, I have taken RF R1 10K, RF 20K. So what is the gain? Is equal to 2 with a negative sign. And here I have taken a resistor which is a parallel combination of 10 and 20 equal to 6.8. Right? I have connected a red line to the input terminal and a blue line to the output terminal. Right? And the input I have given from a signal is a sinusoidal signal I have given, 1 kilowatt sinusoidal signal. Right? Let us run this and see how it works. See, this is the input is a red line, right? And input 1 volt per division, output is also 1 volt per division. You see, there is a straight gain of 2, but there is a total 180-degree phase reversal because of the negative sign. So it is so easy to make an amplifier. That is why nowadays, when in your college you are trying to do any project, etc., whatever it is, hardly anybody will ask you to do it with a discrete transistor, etc., unless there is a special reason. They will always ask you to use an op-amp, right? Next is, this is a non-inverting amplifier. As usual, the input 10K, but inverting input is grounded and non-inverting input is connected to the source. Here also, I have taken a same sinusoidal 1 kilowatt source. Let us say here, what is the gain? Gain is 20 by 10 is 2 plus 1 is equal to 3. Let us see how it works. So this is how it works. Here, the input, you see the input red one and output blue one is in phase because this is a non-inverting. And yeah, input was peak to peak 1 and 1, 2 division. Output is 3 plus 3, 6 division. So there is a gain of 3. So this is so simple to make a inverting or non-inverting amplifier with the help of a op-amp. Next day, we shall see some other beautiful applications. In fact, let me tell you, there are hundreds of very simple and beautiful applications of op-amp, and they are given in your textbook. If you are doing any project work in your BTech course, you can always see all these beautiful circuits given in your textbook and apply any one of them. You will be, if you are using op-amp, you will be very successful. If you're using op-amp and making amplifier, you don't have to do very lengthy calculations and other considerations. Okay. Next day, we shall see some other applications of the op-amp.